In this video, we're going to talk about 15 different Putnam problems and their solutions. And it's going to be insight from all over undergraduate mathematics. The Putnam competition this year is actually this Saturday as of the taping of this video. And even though it's an unofficial contest this year, there's a lot to learn from these problems and solutions. So stay tuned. Welcome to today's video. I'm Prof. Omar. So let's get started with these Putnam problems with the problem from 1995. You have a subset of the real numbers that's closed under multiplication. And you have two disjoint subsets, B and C, of this set A, whose union is all of A. And then you have this property that for B and C, if you take any three numbers in any of the two sets, the product of the three numbers is going to land in the set itself. And the question asks to prove that at least one of the two sets B and C is closed under multiplication. Okay, so we're going to suppose that this wasn't the case. The problem itself makes it seem like that it's going to be the case that a contradiction would work. So say you had B1 and B2 and B, then you would have to have the product being in C if it's not in B. And for C1 and C2 to be in C, the product would have to then fall in B itself. So now we have a triple, C1, C2, and B1, B2, all three in C. The closure of the product tells us that B1, B2 times C1, C2 is in C. And the closure of the product in B tells us B1, B2 times the quantity C1, C2 is in B. Okay, but these two expressions are actually the same thing, and they can't lie in both the sets B and C because the sets are disjoint. So this problem was cool because the statement of what you're trying to prove actually feels like a natural way to do it is by contradiction. And if you do the contradiction and play things out, you're actually able to piece things together to get the contradiction you want. All right, Putnam 1996, we're going to look at this interesting problem where you're asked to prove that the sign of a matrix can never be the matrix 1, 1996, 0, and 1. And here we're assuming the matrix A has real entries. Okay, and we should talk about what the sign of a matrix is. It's actually usually represented in terms of a power series expansion of the matrix. And we won't talk about convergence issues here. But the sign of a matrix is defined to be the sum k equals 0 to infinity, negative 1 to the k, over 2k plus 1 factorial times the matrix A raised to the 2k plus 1 power. Okay, so how do we justify that such a matrix can't possibly exist? So one thing that we could do is try to hone in on our experience from matrices, but maybe we don't know a lot of matrix theory. We do know a little bit of trigonometric identities. Though, so if we let cosine A be the sum k equals 0 to infinity, negative 1 to the k plus 1 over 2k factorial times x to the 2k, that's the power series expansion of cosine, and that x should be a capital A, so we're plugging in the matrix A into the power series. Then sine squared A plus cos squared A is the identity matrix. This is an identity that one can prove. Again, we're not going to talk about convergence issues. And we know that the sine squared A is the square of the matrix that we have, which is the matrix 1, 1996, 0, 1. So we can square this matrix to see what this is. And it turns out to be, so the first product is still a 1. And then we get two copies of 1996, a 0, and then a 1. Okay, so then that tells us that the quantity cosine squared A is this matrix that has a lot of zeros in it and some non-zero term in the top right corner. Now, it turns out you can never have the square of a matrix whose entries are real looking like this, where you have 0 everywhere except for the top right corner. There are actually a lot of interesting theoretical reasons why, but we're going to just prove this directly by looking at a generic matrix and seeing what happens. So say you had a matrix A, B, C, D, and you square it, and your hope is that it looks like what we have for cosine squared. So 0, 0, 0, except for on the top right corner, asterisk meaning some non-zero term. Okay, let's expand this product. On the diagonals, we'll have a squared plus bc in the top right, and on the bottom right, we'll have d squared plus bc. Okay, and then the other terms will have ab plus bd, and then we'll have ca plus dc. And we can factor out a b and a c from the two terms that are not on the main diagonal. So the top will get b times the quantity a plus d, and the bottom will get c times the quantity a plus d. Okay, so we're given here that if we have a matrix A, B, C, D that we can square to get the matrix on that right, then the quantity b times a plus d is non-zero, whereas c times the quantity a plus d is 0. Okay, so if b times a plus d is not 0, then c times a plus d is 0, so c has to be 0. Okay, but then a squared plus bc is 0, which then tells us that a is 0, and d squared plus bc is 0, which then tells us d is 0. So a and d are 0, which actually tells us that a plus d is 0, which means that top right corner, b times the quantity a plus d actually is 0. So that's a contradiction. There's no way we can have a matrix whose square looks like this. If you want to learn more about sort of more direct theoretical reasons for this, I would suggest looking up nilpotent matrices and their properties. Right? So again, a plus d is 0. That contradicts that the quantity b times the quantity a plus d has to be non-zero. So such a matrix doesn't exist. The next problem is the Putnam 1997, which asks us to find out whether or not the number of positive integers ai, 10 of them, where the sum of the reciprocals is 1, is it an even number or an odd number? So there's an odd number and even number solutions. Okay, so if we had a solution where a1 and a2 were different, then we could swap a1 and a2 and get a new solution. We'll get a different pair. So we can pair things up if a1 and a2 are not equal. And so if we're interested in the number of solutions, whether or not the number of solutions is odd or even, we can look strictly at the solutions where a1 and a2 are equal, because the other ones pair off. And similarly, we can assume a3 is a4, and a5 is a6, and a7 is a8, and a9 is a10. So we've simplified this to having less variables. The parity of the number of solutions of our original equation is the same as the parity of the number of solutions to 2 over a1 plus 2 over a3 plus 2 over a5 plus 2 over a7 plus 2 over a9 is 1. Okay, so now we want to find out the parity, even or odd number, of the solutions of this thing. And we can do the same thing. If a1 and a3 were not the same, we could interchange a1 and a3 to get another solution, so we can pair those off. So we can assume a1 and a3 are the same, and similarly that a5 and a7 are the same. Okay, if we do that, then we'll have that this equation, the parity of the number of solutions is the same as the parity of the number of solutions of 4 over a1 plus 4 over a5 plus 2 over a9 is 1. Okay, we can do this one more time now with the remaining two variables. If a1 and a5 are not equal, we could interchange a1 and a5. That pairs solutions up. So the parity of the number of solutions is the same as that of 8 over a1 plus 2 over a9 is 1. And we can actually find out the number of positive integer solutions to this thing. So let's, for simplicity, let x be a1 and y be a9. Then we can write this equation as 8 over x plus 2 over y is 1. So we can multiply here by xy, and we'll get 8y plus 2x is x times y. And then rearrange, we'll get x times something and y times something equals 0. Now, we can put a negative 8 to match with the y when we bring the 8y over, and a negative 2 for the x, but then that gives us an extra 16, so we have 16 times the quantity x minus 8 times the quantity y minus 2. Or x minus 8 times y minus 2 is equal to the quantity 16. Okay, so to find out the solutions to these, where x and y are positive integers, we can compare factors of 16. So I'll let you do this and leave your thoughts in the comments. It turns out there are exactly 5 positive integer solutions, and so our original equation has an odd number of solutions as well. So this is a really cool problem because we were able to figure out the parity of the number of solutions without actually finding the number of solutions in the first place by using this pairing up argument of variables. And this is a very cool technique to use when you're asked for things like whether or not you have even number or odd number of solutions in something. Okay, Putnam 1998. You're given 3 points, A, B, C, in the plane with integer coordinates. And you're also given that the length AB plus the length BC all squared is strictly less than 8 times the area of ABC plus 1. And you're asked to prove that A, B, C are vertices of a square. Interesting. Okay, let's look at this quantity AB plus AC all squared. So we have that AB, this quantity is the same as AB squared plus 2AB times BC plus BC all squared. Okay, so maybe we know some lower or upper bounds for this. We're given that there's an upper bound of 8 times the area of ABC plus 1. But we actually know a little bit about this quantity from a geometric perspective. Okay, so first of all, if we look at AB squared plus BC squared, by the arithmetic geometric mean inequality, that's greater than or equal to twice their product. And then the middle term is twice their product, so this whole thing is greater than or equal to 4 times the product of AB and AC, or AB and BC. All right, but we also know a little bit about the area of ABC in terms of those two side lengths. It's half times the length of AB times the length of BC times the sine of the angle subtended by the vertex B. So this AB times BC product is going to be then greater than or equal to twice the quantity ABC because sine theta is less than 1. So this quantity is actually greater than or equal to 8 times the area of ABC. So we see that the expression here, the square of AB plus BC, is sandwiched between 8ABC and 8ABC plus 1, the area of ABC. And it actually has to be an integer quantity that we have. So let's take a look at this. So if you have 2 points, x, y, and say AB, with integer coordinates, then the area of that given triangle is half times the quantity that's the determinant of the 2 by 2 matrix you get with the vertices. So it's XA, the absolute value of XA minus, and that should be BY. Okay, and since we have integer coordinates, that means that 8 times the area has to be an integer value. So 8ABC is an integer, and 8ABC plus 1 is also an integer. So if this quantity that's sandwiched in between two integers is strictly less than an integer and then is greater than or equal to the integer before it. Okay, we also have another sandwich inequality here, which is that AB squared plus 2ABBC plus BC squared is at least AB squared plus BC squared plus 4ABC from the area formula we had before. So, since the expression that we have is sandwiched between these integers, we get that AB squared plus BC squared is equal to 4 times the quantity, the area of ABC. And the area of ABC is then twice AB times BC times the sine of theta, as we were given in the general problem. Okay, and this first equality that we had came from the red sandwich inequality compared to 8 times the area of ABC. All right, but AB squared plus BC squared is greater than or equal to twice AB times BC. So sine theta is forced to be 1 because it's at most 1, and we need this inequality to hold. So theta is actually 90 degrees. So we do have a right angle at B. And I'm going to leave you to think about thoughts in the comments for why you're forced to have vertices of a square and not just a rectangle. So leave your thoughts in the comments for that. So this is a really interesting problem. It's actually at the end of one of the sections of the Putnam, and it has a lot of roaming pieces. I think one of the biggest lessons is knowing that if you have integer vertices, then you get an area that's half an integer. Okay, so the next question is Putnam 1999, and it's this double sum, m equals 1 to infinity, n equals 1 to infinity, of m squared n over 3 to the m times the quantity n 3 to the m plus m 3 to the n. Now the first thing to notice here is you have two m terms on the top and an n on the bottom, which you can bring into the denominator to make things more symmetric. If we divide the 3 to the m by m, and then the thing in the parentheses by m over n, we get a much more symmetric sum. It's the double sum over the two variables of the following quantity. If we make things simpler and let x be 3 to the m over n and y be 3 to the n over n, I mean, technically we should index these like x sub m and y sub n, but we'll ignore that. We get the sum, double sum, 1 over x times the quantity x plus y. Okay, now if we interchange the role of m and n, we'll get the same double sum because of the symmetry of what we have in the picture. So the double sum is also equal to the double sum of 1 over y times the quantity x plus y. Okay, cool. So by that symmetry, we can represent the whole double sum as half the sum of this symmetrized version, which is 1 over x times the quantity x plus y plus 1 over y times the quantity x plus y. And an advantage to do that is we're really honing in and using all of the symmetry that's given to us. Okay, so if we add these two quantities, we'll find a common denominator of xy times the quantity x plus y. We put things together, and something kind of magical happens. We have x plus y in the numerator, and then we have xy times the quantity x plus y in the denominator, and the two x plus y's divide each other out to give us a 1 over xy. Okay, so now we can figure out this double sum by figuring out what half the double sum of 1 over xy looks like. And that's a little bit simpler than the expression that we were given. So let's make the substitution and see what this looks like. So this is half the sum n equals 1, or m equals 1 to infinity, and then the other variable to infinity of m over 3 to the m times n over 3 to the n. And these two different expressions are independent of the other one's variable. So this is the sum n equals 1 to infinity of n over 3 to the n all squared. Okay, so we're left with this sum, and there's a lot of ways to compute the inner sum. I'm going to show a way where we don't technically prove that the sum converges. You can prove the sum converges using things like the ratio test. But the way we're going to establish a sum is thinking about it as a sum of different geometric series. So you have one copy of 1 over 3, and then you have two copies of 1 over 9, 3 copies of 1 over 27, and 4 copies of 1 over 81, etc. And this sum goes on forever. Okay, so we can think about this as adding in each column. So the first column is 1/3 times the sum 1 plus 1/3 plus 1/9 plus etc., which as an infinite geometric series sums to 1 over 1 minus 1/3. We're going to let x be 1 over 1 minus 1/3. Then the next column adds to 1/9 x, because we can pull the 1/9 out and get the same geometric series. The next column adds to 1 over 27x, etc. So our total sum is, if we factor out the x, 1/3 plus 1/9 plus 1/27, etc., all times x. But the thing in the parentheses can be represented in terms of x as well. It's 1/3 times x itself. Okay, so our final sum then is 1/2 times all this quantity that we have over here, which is 1/3 of x squared, all squared, right? And that works out to, that should be a 12th, not a 6th, a 12th of the quantity x to the 4th. X here is 3/2, it's 1 over 1 minus a third, and that works out to 9 over 32. So I think the big lesson with this problem is really, when you look at a sum like this, it looks kind of wild, but use the symmetry at hand. Okay, Putnam 2000, we're going to look at this problem here, which asks us to prove if n and m are positive integers with n greater than m, to prove that the GCD of mn all over n divided or multiplied by the binomial coefficient n choose m is an integer. Now, the thing is, you might be tempted to take m and n and factor them, but then that gets really quite annoying. Instead, this is a great time to use what's called Bézout's identity, which tells you that you can represent the GCD of two positive integers as an integer combination of the original integers. So there are integers a and b, so that the GCD of m and n is am plus bn. This is going to be really helpful in trying to show that the expression is an integer. One of the reasons is a part of this will cancel out quite quickly. So if you write down this expression over n times n choose m, we get am over n times n choose m, and then we get bn over n, which is just b. So you get b times n choose m. B times n choose m is an integer from what we know quite quickly, because b is an integer and n choose m is 1. So now we need to deal with this, the first expression. We can write n choose m as n factorial over m factorial times the quantity n minus m factorial. So we can expand that out and cancel the m and n. N factorial is n times n minus 1 factorial, so that'll help get rid of the m. And m factorial is m times n minus 1 factorial. So we can divide those with the m and n to get an expression that's actually n minus 1 choose m minus 1. So our expression we had that was a m over n choose m can be represented as a times n minus 1 choose m minus 1. And now we have that that's an integer because a is an integer. So this is a great use of Bézout's identity. And there's a video that I made before about Bézout's identity if you want to know a little bit more about that. Definitely highly suggest checking that out. Okay, the next problem is from the 2001 Putnam. And it says the following. You have an operation star and a set S. And anytime you have two elements in S, AB, A star B is an S. And you also know that if AB is an S, then A star B, star A is B. And you're asked to prove that if AB is an S, then A star B star A is B. So I want to look at the actual expression we're given and look at the roles. Let's underline the B's and put a box on the A's. So what we're saying here is that anytime you have something in a box and you have something underlined, that expression you get is B. So we'll put the B star A in a box, and from what we're given about this operation, box star the double underlined, which is B, star the box is B. There's our underlined B, and then the B star A is our box. Okay, so that mimics what we're given about the expression. Okay, so now the question is what we do with this expression B star A star B. And now you can think about this in a different way. You can think about this as the expression we're given with A and B interchanged. So B star A star B is actually A, and that gives us the conclusion that we want. So that was a bit quick, but I think the big thing with this is when you're given an operation that's random, like a star operation like this, box and underline your different variables to get a sense of what's happening generically. Putnam 2002. So this problem asks, if you have a positive integer n, let t sub n be the number of non-empty subsets of the set 1 through n with an integer average. You're asked to prove that t sub n minus n is even. Okay, so every subset that has exactly one element in it has an integer average. It's the average of the one number that you're given. So t sub n minus n, which we'll call s sub n, is the number of sets with at least 2 elements in them and with integer average. Now, like a problem we saw earlier in this video, if we're trying to prove something's even involving sets, it's good to pair sets off. So let's think about a natural way to pair sets in this setting. So let's say you have a set S that has an integer average, and let's call the average M. So it could be that M is in the set or not. If M is in the set, we can pair M with the set where we get rid of that average M. And the average in that set is still going to be M. Similarly, if we have a set where the average is not an M, we can throw the average in. And then that will be a new set that has an average of M. And this is an involution, meaning if we apply this to the result of a set, like we throw M out and then put it back in, we get the original set back. And so this gives us an actual exact pairing of these sets with integer averages, and so the averages have to be, the number of such sets has to be an even number. And so we get that T sub n minus n is even. I really like this idea, right? So again, it was mimicked in a different problem. Pair things up if you're trying to prove a number, the number of things you're counting is even. Okay, the next problem is Putnam 2003. We have a bunch of non-negative real numbers, and you're asked to prove that the product of the AI's raised to the 1 over n plus the product of the BI's raised to the 1 over n is less than or equal to this huge product here raised to the 1 over n. It's the product of the sums of the AI's and BI's paired. So we'll raise each side to the n here, and that'll have the product of pairs on the right side, and then on the left side we'll have the AI's to the 1 over n plus the BI's to the 1 over n all raised to the n. So we're trying to compare these two expressions right over here. Okay, so we can do that by comparing the kth term of the expansion, thinking about the thing we raised to the n on the left-hand side as a binomial. We have a thing plus a thing raised to the n, and comparing it to the kth term of the expansion of the right side. So let's look at the right side and look at the terms with exactly k a sub i's in it. So we'll have the sum I1 through ik, subset of 1 through n, of a sub I1 times a sub I2, dot, 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 up to a sub ik. That's a random generic k term, AIs. And then we have n minus k of these bj's. So we'll have bj1, bj2 up to bjn minus k, where j1 through jn minus k is like the complement of the indices of the AIs. And we're trying to find a lower bound on this that hopefully it gives us the lower bound that we want in our expression. So we can get a lower bound by taking the product of the terms. A lower bound is n choose k times the product of the terms raised to the n over k, 1 over n, or 1 n choose k by the arithmetic geometric mean inequality. The sum of terms is going to be greater than or equal to the number of them times their geometric mean. Okay, so the number of times AI appears is n minus 1 choose k minus 1. The reason is if you look at a specific I, the number of times AI appears is, well, we have to fill out the rest of the A terms, of which there are k minus 1, with anything but the term AI. So that's k minus 1 choices. So we get n minus 1 choose k minus 1 times that the AI appears in this entire sum star. Similarly, bj occurs n minus 1 choose n minus k minus 1 times. So the sum is greater than or equal to n choose k, the number of terms, times like a1 to the n minus 1 choose k, and then to the 1 over n choose k, because we'll have that 1 over n choose k when we do the arithmetic geometric mean inequality. And that fraction, n minus 1 choose k minus 1 all over n choose k, is k over n. The binomial coefficient n minus 1 choose n minus k minus 1 all over n choose k for the b's works out to be n minus k over n. And so the sum we have star is greater than or equal to n choose k times the product of the AI's raised to the k over n times the product of the j's raised to the n minus k over n. And that actually is exactly one of the terms in the expansion of the binomial expansion of that left-hand side. It's the kth term when we take the first part raised to the k times the next part raised to the n minus k times n choose k. So a nice systematic way of taking things one by one in this expansion that seems like it's quite horrible, but is somewhat manageable to deal with. Another type of problem that's sort of similar but not as complicated as the previous one is Putnam 2004, which asks to prove that m plus n factorial over m plus n to the m plus n is strictly less than m factorial n factorial over m to the m n to the n when m and n are positive integers. This looks like a complete mess when you start off, but if you divide things so that they match and look like familiar quantities, it helps. So we'll divide the m factorial and n factorial to get this expression on the right, and then multiply by m plus n to the m plus n to get this expression on the right here. And so we're trying to prove what we have on the right here is greater than what we have on the left. Now the thing on the left we can actually write in terms of something we know. It's m plus n choose m. Okay, now on the right we have the quantity m plus n raised to the m plus n, and we can expand that using the binomial theorem. One of the terms is going to have m raised to the m, and then n raised to whatever exponent is left, which is n plus m minus m, which is n. And the coefficient is going to be n plus m choose m. And there are many other terms in the binomial expansion of the quantity m plus n raised to the m plus n. Okay, but if we divide this one term by m to the n to the n, we get exactly the binomial coefficient on the left. And so the term on the right actually is much, much, much larger than the term on the left. So I think the key here is to match the factorials up so you have like a binomial thing, and then you can do analysis that way. Okay, Putnam 2005. So this problem I really, really like. It gives you positive integers m and n, and asks the following question. It constructs a function f that counts the number of integer tuples x1 through xn whose absolute values sum to something less than or equal to m, and then asks you that this function is symmetric. So in other words, the number of n tuples whose absolute value add to something less than or equal to m is the same as the number of m tuples whose absolute values add to something less than or equal to n. To make things easier, we're going to define f of 0m and f of m0 for different values of m to be actually 1. And then maybe to make things a little bit more symmetric with what's going on, we'll say f of m0 and f of 0n is 1 regardless of what m and n are. Okay, this won't change anything for what we're trying to do. So now the question is how to handle this. And one nice way to handle this is using generating series. So what we're going to do is construct a function in two variables, g of x, y, as a series, whose x to the m, y to the n term is precisely the thing we're trying to handle, f of mn. And the question is, can we find a closed form for g of x, y that will allow us to prove this symmetric count that f of mn is the same as f of nm? Okay, so let's expand this. So the series is the double series is the sum m equals 0 to infinity, n equals 0 to infinity, x to the m, y to the n, plus the number of expressions that we have, which is the number of n tuples, k1 through kn. I use k instead of x because that'll get confusing, where the sum of the ki's is, that should be less than or equal to m, and then we put a 1 for counting each one of these possible summands. So this is the double sum. We'll interchange n and m and see what we can do with this. We'll have the sum n greater than or equal to 0, or n equals 0 to infinity. And then now we're counting this piece where the ki's are all greater than or equal to m. So we'll fix a particular set of ki's, the set k1 through kn for the fixed n that we have. We'll fix those integers and then count the number of them where you have a positive integer m greater than or equal to the sum of those. So we're keeping track of things in a different way. And we'll have x to the m there. Now, this m will then run from the sum of the absolute values of the ki's onward. So we'll get a sum like x to the a plus 1, etc., which we can write as a simpler expression as k to the a all over 1 minus x as a power series. So we can replace that entire sum that we have there with x to the sum of the absolute values of the ki's, that's our first term that will appear, all over 1 minus x. Okay, now outside of the sum over the ki's, we're missing a y to the n. That's the term that we had in our original series. We're going to add that back in a little bit later because we just forgot to write that down. Okay, so we can take the 1 minus x out of the entire expression. There's nothing involving that variable. We have the sum n equals 0 to infinity, and then the sum of x to the ki ranging over all possible integers ki. So ki here is any possible integer we have and then raised to the n. The reason is because we have k copies of x to the ki, right? And each of these sums are separate from each other. They're independent of each other. We're summing over all k1, k2, all through kn in the integers, and then we're summing the k to the exponents of them. We can do that by a product of each of the individual ones. Okay, so what does this sum look like? So we have x to the 0, and then we have x to the 1, and then x to the absolute value of -1, which is x, etc. So we can separate this into two sums, 1 plus x squared, etc., and then x plus x squared plus x cubed, etc. Those have series 1 over 1 minus x and x over 1 minus x. Putting that together, we get 1 plus x over 1 minus x. Okay, so here's our expression for a closed form for our sum in terms of x and y. We get this 1 over 1 minus x times this entire sum, which is the quantity y times 1 plus x over 1 minus x all raised to the n from 0 to infinity. And that simplifies as a series as 1 over 1 minus the quantity y times 1 plus x over 1 minus x. And if you simplify this algebraic expression in terms of x and y, you'll actually get that it's 1 minus x minus y minus xy, which is symmetric about the variables. So g of xy is actually the same as g of yx. Okay, so if the series are the same when we interchange the role of x and y, that means that the counts of the fm and fn are interchangeable as well. So we get exactly the quantity that we wanted. So an interesting application of generating series, if you want to see more about generating series, I actually have a playlist right over here that you can watch and learn a lot of fascinating things about not only how to solve problems with them, but also how they work in general and how they're useful. And the fact that we don't have to worry about convergence. You can make an argument that convergence will happen. You can prove, I think, that when the absolute value of x and y are less than or equal to a fourth, you're fine. Putnam 2006. Let's look at the set of continuous functions f from 0, defined on 0, 1 to the reals. And the question is to find the maximum possible value over all such functions of this integral, the integral from 0 to 1 of x squared f of x minus x f of x squared dx. Now, if we look at this function here, x squared f of x, we can actually augment x f squared to include it by having x times the quantity f of x minus some expression. Now, to make that work out, we need an x times f of x, which we can get by putting a negative x over 2 there. But then we'll end up with a new function that we need to balance to get no term independent of f. and that will be x cubed over 4. So we have to write down an x cubed over 4 as well. So this expression we have can be written as x cubed over 4 minus something that is non-negative because it's a square. So this is going to be less than or equal to the integral from 0 to 1 of x cubed over 4 dx. We can compute this integral, which works out to a 16th. And so 16th is an upper bound, and we can force that upper bound by making the expression that we were squaring equal to 0. We can do that by letting f of x equal x over 2. So it's kind of a quick solution, but the idea really is to balance things so you get some quantity that you're subtracting that's always non-negative and force to be actually 0 at some point so that you know equality occurs. Putnam 2007. Find the least area of a convex set intersecting both branches of the hyperbolae x equals 1 and both branches of the hyperbola x, y equals -1. So this convex set is going to have at least 4 points. And since it's convex, we can minimize the area by minimizing the area of a 4-point convex set. If it had more points, we'd have that 4-point convex set inside of a bigger convex set. So we'll maximize the area of some convex set that has 4 points, one from each branch. Or minimize, sorry. We'll pick A to be A 1 over A in the first quadrant. Then we'll pick B in the second quadrant, where the little b is a positive number. So then the point will be -b 1 over b. And similarly, we'll put points in the other two quadrants, where our variables little c and little d are all positive. So the coordinates are written in the way that they're written to match the quadrant that each of the points lie in. Okay, and so our set we're dealing with is this quadrilateral right here, and we're trying to find the least possible area of that quadrilateral. So we'll draw a diagonal like this, and then draw two vectors that'll let us represent the area in terms of cross products of the vectors emanating from A and the vectors emanating from C. So let's write down each of these vectors. So the vector AB is minus B minus A, and then 1 minus B minus 1 over A. And then we have the same thing going on for all of these other vectors, the one emanating from A to D, and then the one emanating from C to D and C to B. Okay, so when we write down these four vectors like we're doing now, the thing that we have potentially some familiarity with and will use is the fact that if we want the area of the triangles that we just drew that split the convex set into two pieces, the area of those two, any one of those triangles, is half the absolute value of the cross product. Now, you might not be familiar with cross product. Another way to think about this is if you put the vectors, say AB and AD, in a matrix, it's going to be half the determinant of that matrix. But we have to be careful of the order that we do this in, because if we write a particular determinant down, we may get something that's negative or positive. So here we're actually writing down the determinants, which give the area of the entire parallelogram generated by ABAD, and then separately CBCD. And we've expanded each of these expressions. So here's the expansion of the first one, the positive and -1 cancel. And then here's an expansion of the second one. We notice a lot of negative signs here, and so that indicates the likelihood that we got the orientation wrong. So we'll need to change this up so that we have the negative signs being positive and the positive signs being negatives in the expression of the second thing. Okay, so we'll do that now. Okay, so now the total area then is the sum of all of these things. So the BD and negative BD cancel, and then the DB and negative DB cancel, and we're left with A over B plus A over C plus B over A plus B over C plus C over B plus C over D, and then D over A plus D over C. In every expression here, things work out beautifully so that we have an expression using the arithmetic geometric mean inequality that works out to give us that this entire expression has a controllable lower bound. If we let A be the area is half this expression. And the entire internal thing is greater than or equal to 8 times the product of the entries. And it works out, raised to the 1/8 power, and the product of the entries works out to be 1. So the maximum possible, or the minimum possible area of this quadrilateral is 4. And you can actually achieve equality where you set A, B, C, D all equal to 1. Now, some of these fractions in the final area, one of them needs to be augmented so that there's another D in the denominator. I'll leave you to think about in the comments what that expression ought to be, but it works out to be something that is symmetric. Putnam 2008, this is a really cool question that I really like. So it's a game about a 2008 by 2008 matrix. Barbara and Alan play the game. Alan goes first. Alan wins if the final matrix has determinant non-zero. Barbara wins if the determinant is 0. Who has the winning strategy? And each time, a player fills in an entry of this empty matrix. So let's think about this. Alan goes a specific time, so Alan just picks an entry and places an X in. Now, what can Barbara do that's clever? Well, there are a lot of different strategies for Barbara to win, but a key thing that Barbara can notice is if the sum of every single row in a matrix is 0, then the determinant is 0. One way to think about this is all the terms in each row add up to 0, so they lie in a plane. So what Barbara can do is put in a negative X in an empty cell in the same row anytime Alan places an X. That'll make the sum of all the rows 0, and we get a determinant of 0. Okay, our final problem is Putnam 2009, and it's this differential equation that is somewhat complicated. It's a system. And the problem asks you to actually find out what the function f is, given that you have these 3 differential equations and 3 functions. The expression given for f prime, g prime, h prime, and then some initial conditions for f, g, and h. And again, the goal is to find out what f is. So one natural thing to do here is make things symmetric. We'll multiply by the first equation by gh, the second by fh, and the third by fg. Okay, if we do that, then the left-hand side works out to this nice product over all of the functions where we have exactly one of them being differentiated each time. So if you add these all up, we get f prime gh plus fg prime h plus fgh prime on the left side. Now the right side, when we do the multiplication that we had, all the terms end up having a term f squared g squared h squared. So we get f squared g squared h squared times 6, and then we get a bunch of 1s to add up to 6. So if we let y of x be the function f times g times h, the left-hand side is actually the derivative of y. Using the product rule twice, the right-hand side is 6y squared plus 6, and so we can solve for y. There's a nice differential equation for y. So let's actually do the solving. So we can write this as y prime over y squared plus 1 equals 6. The integral of the right side is arctan, so we get arctan of y is equal to 6x plus a constant. And so y is tangent of 6x plus a constant. We can figure out what this constant is by using the initial conditions. We have that f of 0, g of 0, h of 0 all 1. So y of 0 is 1 times 1 times 1, which is 1. So when we plug in x equals 0, we want the result to actually be 1. And tangent of pi over 4 is 1, so we can make the constant c pi over 4, and that'll work. So there we have our function y, which is the product of all 3 functions. But that wasn't our actual goal. Our goal was to figure out what f was. Okay, but at least we have y, and that'll help us figure out f. If we look at f prime, we're given that f prime is 2f squared gh plus 1 over gh, but we know what fgh is. That's our function y. So we actually get an expression if we divide by f. If we divide by f, we get 2fgh plus 1 over fgh. So f prime over f is actually twice our function y plus 1 over y. And we can represent that in terms of trigonometric functions itself. Okay, so 2y is twice tan 6x plus pi over 4, whereas 1 over y is cotangent x plus, or 6x plus pi over 4. And so now we have a differential equation, f prime over f equals this trigonometric expression. So let's actually solve it, and then, or at least get an idea of how we would solve it, and then use that to get toward what this function f itself might be. So we can recognize the left side as the derivative of the logarithm of f. So the natural logarithm of f is whatever the integral of the right side is. And here we need to know how our integrals of tans and cotangents and things like that work. Okay, so this will work out to -2 times the natural logarithm of cosine of 6x plus pi over 4. You can do a substitution instead to figure out that this is going to end up being the case by thinking of tan as sine over cosine. And then plus the natural logarithm of the sine of the same quantity, 6x plus pi over 4. Okay, and that's all going to be divided by 6 because we need to use that chain rule when we have that 6x and differentiate. Okay, so f then is going to be some constant times e raised to that entire expression. And so if we want to figure out what f is, we plug in x equals 0 to figure out what the constant is, knowing that f of 0 is 1. So I won't write that down here, but now we got the essence of the differential equation. And the key here was using the symmetry of the functions and the expressions we had to be able to figure things out. So there we go, a blast through 15 Putnam problems, Putnam Extravaganza. And if you happen to be taking the Putnam 2021 this Saturday, have fun, enjoy the problems, especially since this year's contest is unofficial. You can really enjoy, sit back, relax, and not feel any time pressure. So have fun, enjoy, and if you're seeing this video well beyond the point of the contest, enjoy these different solutions, and I hope you really got some cool insights on different ways to think about different problems from all over undergrad math.